The elephants stopped eating at exactly the same moment. Not slowly, not one by one, all at once. Trunks frozen mid-air, ears fanned out like satellite dishes. 30 animals suddenly locked onto something I could not see, could not hear, could not even guess at. I had my recorder running, I had my headphones on, and I heard absolutely nothing except wind moving through dry grass. Then they ran. Not toward anything, not away from a lion, not away from a gunshot, not away from any threat my very expensive, very useless human senses could detect. They just ran. A wall of gray moving in one direction like they'd all received the same text message at the same second. I was standing in what I thought was a safe gap between two termite mounds. I was wrong about the gap. Yep, that's me. You're probably wondering how I ended up here. Oh, hey there. So, I used to be a field recordist, bioacoustics technically, which is a fancy way of saying I stood in remote places holding microphones trying to capture sounds most people never think about. Whale calls, bat clicks, the low, rolling rumble elephants make that sits below what your ears can register. I spent my career chasing sound, and I died because I couldn't hear the one sound that mattered most. There's a joke in there somewhere. I've had a lot of time to find it. Because here's the thing about being dead, and I promise this is relevant, you get a front row seat to everything you missed while you were busy being alive. No deadlines, no gear to charge, no funding committees asking why you need 6 months to record a bat. Just time, an absurd, uncomfortable amount of time. And I've spent most of it doing exactly what I did before, except now, nothing can trample me. So let's talk about what animals hear that you never will, because it turns out the world is louder, weirder, and far more secretive than your ears will ever let you know. Human hearing runs from about 20 Hz to 20,000 Hz. That's your whole range. Everything outside it, every frequency lower or higher, might as well not exist as far as your ears are concerned, but sound doesn't care about your limitations. It just keeps going. Below your range is infrasound. Above it is ultrasound, and an enormous amount of animal life is having entire conversations in both directions while you stand there, oblivious, taking a nice photo. Which brings us to the animal that got me. Elephants communicate using infrasound, rumbles as low as 5 to 10 Hz, well below what your ears can process. These calls can travel for miles across open terrain, sometimes farther depending on conditions. And here's the part that should really bother you. Elephants don't just hear these calls with their ears, they feel them. Researcher Caitlin O'Connell-Rodwell spent years documenting how elephants pick up seismic vibrations through their feet and trunks, detecting rumbles transmitted through the ground itself. Their feet contain dense fatty tissue and sensitive receptors that respond to vibration, essentially turning the ground into an extended eardrum. An elephant standing calmly in a field might be receiving a broadcast from another elephant kilometers away, and you would have no idea it was happening. This is less big ears, good hearing, and more entire body wired as a subwoofer. Evolution looked at the problem of long-distance communication and said, sure, let's just make the whole animal into a speaker system. Fast Fact 1. A single elephant rumble can carry information about identity, reproductive state, and location. Researchers have recorded elephants responding to the calls of specific individuals from herds they hadn't seen in years. Imagine recognizing a voice you haven't heard in a decade, except the voice was quieter than heartbeat and traveled through solid ground to reach you. So when that herd bolted, they weren't reacting to nothing. They were almost certainly reacting to something, a distant storm, another herd's alarm, possibly a shift in the earth itself. I'll never know exactly what. I was too busy becoming a cautionary tale. Which brings us to something even stranger, because at least elephants have ears. Some animals don't even have that going for them. Let me introduce you to the greater wax moth, an unremarkable-looking beige insect that happens to hold the current record for the highest frequency hearing ever documented in the animal kingdom. Researchers led by James Windmill and colleagues found that these moths can detect sound up to roughly 300,000 Hz. For comparison, dolphins, famous for their ultrasonic hearing, top out at around 150,000 Hz. This moth doubles them. Why would a small, unglamorous moth need to hear frequencies that high? Bats. Bats hunt using echolocation, sending out ultrasonic pulses and listening for the echo. Moths are a favorite snack, so an evolutionary arms race kicked off. Bats getting better at finding moths, moths getting better at hearing bats coming. The wax moth didn't just keep up, it laughed the competition. This is the kind of thing wildlife documentaries almost never mention because it doesn't photograph well. Nobody's filming a beige moth for its ears, but that moth is running detection technology that would make a military engineer jealous, and it's doing it to avoid becoming a bat's dinner.
You're a moth. You're flying through the dark, minding your business, when a burst of ultrasound hits your ears. A bat, closing in, pulses speeding up as it locks onto your position. You have milliseconds. Some moths dive. Some moths freeze and drop out of the air entirely. And some moths, this is my favorite part, click back. Certain tiger moth species, studied extensively by researchers Aaron Corcoran and Jesse Barber, produce their own ultrasonic clicks in response to an attacking bat. For a long time, scientists assumed this was a warning, a chemical defense signal like a wasp's bright colors. But the data told a stranger story. The clicks jam the bat's sonar. They flood the bat's ears with acoustic noise at exactly the moment it needs precision, scrambling its ability to pinpoint the moth's location. Let that sink in. A moth, an insect with a brain smaller than a grain of rice, is running electronic warfare, actual jamming, the kind of thing you'd expect from a fighter jet, not a bug that dies if you flick it too hard. Here's where I have to be honest with you, because I promised I wouldn't make things up just because they're fun. We don't know if the moth is deciding to jam the bat in any conscious sense. What's known is that the behavior is triggered rapidly and reliably by specific acoustic cues, and that it measurably reduces capture rates in experiments. Whether there's any subjective experience happening in that moth's nervous system is, frankly, above my pay grade, and I'm dead, so my pay grade is 0. But before we get there, let's talk about an animal with the opposite strategy. Instead of stacking on more sensors, evolution decided to strip one all the way down. The praying mantis has one ear, singular, located in the middle of its thorax, roughly where you'd expect a belly button if insects had those. Researcher Ron Hoy's research team discovered this in the 1990s, and it upended assumptions about how directional hearing works. Because normally you need 2 ears, spaced apart, to figure out where a sound is coming from. Your brain compares the tiny difference in arrival time between your left ear and right ear to calculate direction. One ear shouldn't be able to do that. The mantis doesn't use its single ear for directional hearing at all. It uses it almost exclusively to detect the ultrasonic clicks of hunting bats while flying. When a mantis is airborne and picks up a bat's echolocation call, it doesn't try to figure out which direction the bat is coming from. It just executes an evasive spiral dive, dropping out of the sky entirely. One ear, one job, and that job is simply bat detected, abort mission, fall now, ask questions later. Myth 1. True or false? More ears means better hearing. False. It's not about quantity. It's about what question your nervous system actually needs answered. The mantis doesn't need to know where the bat is. It just needs to know a bat exists, right now, somewhere nearby. One ear, wired for a single yes or no question, does that job perfectly. This is less master strategist and more tiny caffeinating accountant who only tracks one line item and refuses to look at the rest of the budget. Speaking of terrible decisions, mine specifically, let's go back to the animal that ended my career as a living person and look at the flip side of the infrasound coin. Barn owls have ears at slightly different heights on their skulls. One ear sits a little higher than the other, and the facial disc funnels sound asymmetrically into each one. This isn't a birth defect, it's the design. That asymmetry lets the owl compare not just the timing of a sound between its 2 ears, but subtle differences in loudness from above versus below, giving it something close to 3-dimensional sound mapping. Researchers have demonstrated that barn owls can strike prey in complete darkness using hearing alone with accuracy that rivals visual targeting. A mouse rustling under a foot of snow is not safe. The owl doesn't need to see it. The owl's skull has been quietly engineered into a targeting computer since before either of you were born. Fast fact 2. Snakes don't have external ears at all. No ear canal, no eardrum exposed to open air. For a long time, people assumed this meant snakes were essentially deaf to airborne sound. But research has shown that snakes can detect sound through bone conduction, picking up
vibrations through their jaw and skull, and evidence increasingly suggests they can also sense some airborne sound through vibrations in their body wall and lungs. Their whole body is doing double duty as a listening device, which is somehow worse than regular ears if you think about it for more than 5 seconds. This is where nature gets weird, because sound doesn't behave the same way underwater as it does in air, and an entire category of animals had to solve hearing completely differently. Fish have a sensory system running down each side of their body called the lateral line, a row of tiny receptors that detect changes in water pressure and movement. It's not technically hearing in the traditional sense, but it does a similar job, picking up vibrations, in this case from water displacement rather than air pressure. It lets a fish sense another fish swimming nearby, a predator approaching, even the shape of an obstacle in total darkness purely from the way it disturbs the water. On top of the lateral line, fish also have inner ears containing small calcium structures called otoliths, which detect actual sound vibrations transmitted through water. And some fish take this much further than you'd expect. Atlantic herring can detect sound frequencies up to roughly 180,000 hertz, deep into ultrasonic range, far beyond anything a fish should need for normal fish business. Researchers, including Bob Batty and colleagues, proposed a compelling explanation. Dolphins hunt herring using ultrasonic echolocation clicks, and herring evolved the ability to hear those clicks coming. To put that in perspective, that's roughly 9 times higher than the upper edge of human hearing. A silver fish smaller than your forearm can detect a predator's biological sonar system before the predator even fires a shot, using a range that would make most human-designed sonar equipment jealous. And that's only half the story, because some animals aren't just avoiding ultrasound, they're screaming in it on purpose, just to be heard. Meet Amelops tormotus, sometimes called the concave-eared torrent frog, native to fast-flowing streams in China. Streams like that are loud, a constant roar of rushing water that drowns out low-frequency sound. Most frog calls would be completely useless in that environment. So this frog does something almost no other frog does. It calls using ultrasonic frequencies, well above the range most frog predators, and definitely you, can hear, cutting straight through the noise of the water. Researchers led by Albert Feng documented this species using frequencies extending past 30,000 hertz, essentially finding an empty channel on the radio dial where the competition, the river itself, couldn't interfere. Evolution didn't fight the noise. It just moved the entire conversation somewhere the noise couldn't follow. Myth 2. True or false? Loud environments prevent animals from communicating effectively. False, and this frog is Exhibit A. When one channel gets jammed by environmental noise, animals don't necessarily go quiet. Some shift frequency entirely, moving the conversation to a part of the spectrum the noise doesn't reach. It's the biological equivalent of realizing the office is too loud for a phone call, so you just start texting instead. But before we get there, I want you to imagine walking through a forest, because you're about to realize how much you're missing. You take one step forward, off the trail, into what looks like an ordinary patch of woods. Birds are singing, a breeze moves the leaves. To you, this feels quiet, mostly. Peaceful even. It is not quiet. It is not peaceful. It is one of the busiest acoustic environments on the planet, and you're deaf to nearly all of it. Above you, bats are shouting at frequencies loud enough to damage human hearing if you could actually perceive them at full volume. Some echolocation calls exceed 120 decibels at close range, comparable to a chainsaw, except pitched so high your ears simply don't register it as sound at all. Below your feet, insects are transmitting vibrations through plant stems. Around you, in that quiet patch of woods, is a screaming, humming, clicking, thumping conversation in frequencies you were never built to hear. You didn't walk into silence. You walked into a party you weren't invited to, because you don't have the right ears to get past the door. Spiders don't have ears, not in any conventional sense. But researchers, including work led by Ron Miles and Ron Hoy, discovered something remarkable about orb-weaving spiders. Their webs can function as an extended auditory system. The silk threads are so sensitive to air vibration that they physically move in response to sound waves, and the spider, sitting at the center, feet resting on the strands, can detect those vibrations well enough to respond to sound sources meters away, far beyond what the spider's own body could sense on its own.
The spider essentially outsourced its hearing to a piece of architecture it built itself. Imagine building a house that also functions as a hearing aid, except you build a new one every few days because the old one got destroyed by a moth. This is the kind of overlooked detail that never makes it into wildlife documentaries because a web just looks like a web. Nobody's zooming in to explain that it's secretly a satellite dish. Fast fact 3.
Cats can hear frequencies up to roughly 64,000 Hz. Dogs top out around 45,000. Both ranges exist largely because their ancestors hunted small rodents, and rodents communicate, including distress calls and social signals well into ultrasonic territory that's completely silent to you. Your dog isn't ignoring you when it suddenly perks up at nothing. Statistically, it's very possible it just heard a mouse having a conversation somewhere in your walls. Speaking of rodents, this next one might be my favorite fact in the entire script, and I say that as someone who has had centuries to develop favorites. Rats produce ultrasonic vocalizations, typically in the range of 50,000 Hz, during positive social interactions, including, according to research pioneered by Panksepp, something that looks remarkably like laughter during play and tickling. Panksepp's team found that young rats emit specific high-frequency chirps when playfully tickled by researchers, chirps distinct from their distress calls, and that rats would seek out the hand that tickled them, suggesting the experience was at minimum positively reinforcing. Whether this constitutes laughter in any sense comparable to human laughter is genuinely debated among scientists, and I want to be careful here. This is an area of active research and interpretation, not settled fact, but the behavioral evidence for some form of positive vocal signaling during rat play is well documented. There is an entire layer of rodent social life, laughter, distress, mating calls happening in your walls, your basement, your backyard, at a pitch your ears were never built to register. The world's most common mammal has been quietly having emotional experiences directly above your head this whole time, and you've heard none of it. Here's a problem for you. To locate the direction a sound is coming from, an animal typically needs ears spaced far enough apart that sound arrives at each one at a measurably different time. That's how your two ears, spaced roughly 6 inches apart, let you tell whether a voice is coming from your left or your right. Now imagine trying to do that with two ears spaced less than half a millimeter apart. Physically, that shouldn't work. The time difference is too small to detect. Nobody told the fly. Ormia ocratia is a small parasitic fly that locates crickets by listening for their mating songs in order to lay eggs on them, which is, to be fair, a genuinely unpleasant fate for the cricket. Researcher Ron Hoy and colleagues discovered that despite ears so close together they should be functionally useless for direction finding, the fly locates singing crickets with startling precision. It turns out their eardrums are mechanically coupled by a tiny seesaw-like structure, amplifying microscopic timing differences into something the fly's nervous system can actually use.
This discovery was significant enough that engineers have used it as inspiration for designing extremely small, highly directional microphones for hearing aids. A fly, smaller than a grain of rice, solved a physics problem well enough that humans copied its homework. Evolution looked at this idea and somehow approved it, and then a few million years later, we just took the notes. Not every animal that lives in a vibration-rich environment develops great hearing. Naked mole rats, for instance, live almost entirely underground in a world dominated by touch and vibration, yet their hearing is relatively poor compared to many surface-dwelling rodents. Living underground didn't push their hearing to superhero levels, it pushed other senses forward instead, touch and chemical communication in particular, while hearing quietly took a back seat. Evolution isn't obligated to maximize every sense just because the environment technically allows it. Sometimes it just shrugs and invests somewhere else. Which brings us to something even stranger, an animal that doesn't so much listen for sound as manufacture an entire mood with it. Kangaroo rats, small desert rodents, have unusually large auditory bullae, bony chambers around the inner ear that amplify low-frequency sound with remarkable sensitivity. Research by scientists including Rulon Clark and others has shown this gives them an early warning system specifically tuned to the low-frequency sounds produced by rattlesnake strikes and owl wing beats, both extremely fast, low-pitched events that would be nearly silent to a less specialized ear. In behavioral studies, kangaroo rats have been observed reacting to a striking rattlesnake with defensive kicks and jumps fast enough to avoid the strike in a meaningful percentage of encounters, reaction times on the order of tens of milliseconds. That's faster than you can consciously register a flash of light. You thought you'd outsmart a creature that's been practicing this for millions of years. Spoiler, you probably wouldn't have a chance.
American alligators produce extremely low-frequency infrasonic bellows during courtship, frequencies so low that some of them fall below what human ears can detect entirely. Yet the vibration is strong enough to make the water directly above the alligator's back visibly ripple and jump, a phenomenon researchers and wildlife photographers have documented and nicknamed the water dance. You can watch water bounce off an alligator's back like it's sitting on a subwoofer, produced entirely by a sound too low for you to hear, using a call other alligators can detect from a significant distance across a swamp. Myth 3. True or false? Infrasound is too low to actually matter or do anything meaningful. False, obviously. The water dancing on that alligator's back should settle the argument on its own. Low frequency doesn't mean low impact. It often means long distance, because low frequencies lose energy more slowly as they travel, letting them carry information across miles of terrain, or, in the case of the ocean, across ocean basins. Sharks don't have visible external ears, but they have a keenly sensitive inner ear combined with a lateral line, tuned especially well to low, irregular frequencies, roughly in the range of 20 to 300 Hz, that mimic the erratic movement of an injured or struggling fish. Researchers studying shark behavior have found that playing these specific irregular pulse patterns underwater reliably attracts sharks from significant distances, sometimes before any scent trail would have reached them at all. This is not a coincidence. It's a targeted evolutionary tool. Sharks are, essentially, wired to respond to the acoustic signature of vulnerability. It's an efficient, if slightly unsettling way to find a meal before wasting energy swimming towards something that turns out to be fine. Blue whale calls can register around 188 decibels at the source, louder at the point of origin than a jet engine, and can potentially travel over vast distances through deep ocean channels under the right conditions, though rising ocean noise from shipping traffic has measurably reduced the effective range of whale communication over the past century. To put that scale in perspective, imagine having a conversation with a friend by shouting from one end of a very large city to the other and having them hear you clearly, except stretched across an ocean, using sound produced by an animal with no hands, no tools, and no idea it might be one of the loudest natural sound sources on the planet. Pigeons are sensitive to infrasound, capable of detecting frequencies well below human hearing range. What researchers still debate is exactly why. One hypothesis, explored by scientists studying avian navigation, suggests pigeons might use infrasonic microseism, extremely low-frequency ambient sound generated by ocean waves, wind patterns, and geological activity, as one of several possible cues in long-distance navigation, essentially listening to a constant, quiet hum produced by the planet itself. I want to be clear that this remains a hypothesis, not a settled conclusion. Navigation in pigeons appears to involve multiple overlapping senses, and infrasound's exact role is still being worked out. Still, sit with that for a second. It's possible that a bird sitting on your windowsill can hear the ocean, the wind, and the rumble of the Earth's crust all quietly humming in the background of its entire life, and it's just never had a way to tell you about it. I had a very good pair of ears for a human, professionally trained even, and it still wasn't enough, because the animal that ended my career as a living person wasn't being sneaky, it was being loud, just in a language I never had the hardware to receive. So here's what I'd tell you if I could go back and interrupt myself standing between those two termite mounds with my headphones on and my confidence entirely unearned. 1. Silence to you means outside your range. Assume there's more happening than you can detect, especially outdoors. 2. If animals around you, birds going quiet, herd animals bunching up, pets suddenly alert, start behaving strangely for no visible reason, take it seriously. They may be responding to something real, well before it becomes obvious to you.
3. Elephants react to infrasound and ground vibration long before visible danger appears. If you're near them and they shift suddenly as a group, move away calmly. Don't wait to see what they saw. You can't hear what they heard. 4. A quiet forest is not an empty one. Understanding that changes how you experience wildlife, even if it doesn't change what you can technically detect. 5. Ultrasonic rodent repellent devices, the ones marketed for pest control, work inconsistently at best, largely because many rodents habituate to a constant frequency fairly quickly. Don't spend money assuming a gadget replicates what evolution spent millions of years fine-tuning. 6. If you keep a cat or dog, understand that a huge portion of its alertness to nothing is very likely something. Respect that, rather than dismissing it. 7. Near water, rivers, swamps, coastlines, remember that fish, alligators, and other aquatic animals are receiving an entire layer of vibration and sound information you're not. Don't assume calm water means a calm environment underneath it. 8. Curiosity about the parts of the world you can't perceive is not a weakness. It's the only reason anyone ever discovers any of this in the first place. I only found out how much I was missing by dying and getting unlimited time to actually pay attention. I'd trade the unlimited time back in a heartbeat, honestly. But since that's not on the table, I'll keep doing this instead. Wandering around, watching the parts of nature that never made it into any film I ever watched while I was alive, narrating it to whoever happens to be listening. Turns out, being dead has decent seats for wildlife viewing. Nobody tells you that part. Anyway, that's the sound of the world you're standing in right now, whether you can hear it or not. Try to listen a little harder. It clearly matters. It's the reason you're watching a ghost talk about moths instead of me watching you. If you want more videos like this, subscribe.